The Brachistochrone problem is a hugely important problem in the world of variational calculus, and therefore in the world of classical mechanics too. This problem was first posed as a challenge by Johann Bernoulli, and it was more than just a problem that he posed. I mean, there was far-reaching politics behind this. The meaning of the word Brachistochrone comes from the ancient Greek meaning shortest time, and it describes a problem in which we're given 2 points. We'll call the first A at a location x1, y1, and B at a location x2, y2. And the idea is that under the influence of gravity, what is the shape of the curve between the 2 points that would cause, say, a marble rolling down that slope to get from A to B in the shortest time? And following one's intuition, one might use as the starting point a straight line, because after all, a straight line is the shortest distance. So the idea is if we have a marble here, say, that's rolling down this frictionless path under gravity, can we perhaps find a better, a more optimal path that will cause this marble to get from A to B quicker? So let's have a look at the actual statement of the problem as it was originally stated. Given 2 points A and B in a vertical plane, what is the curve traced out by a point acted on only by gravity, which starts at A and reaches B at the shortest time? And the idea is that we might consider a whole assortment of different paths. Can we determine which one of these paths would take the shortest time? Back in the 1600s, the late 1600s, the mathematicians of Europe believed that they were the smartest in the world. And it was not uncommon for mathematicians to pose problems in publications as a way of advancing research. In the case of the Brachistochrone problem, the problem was posed by Johann Bernoulli in 1696 with an announcement that went as follows. I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem whose possible solution will bestow fame and remain as a lasting monument. Following the example set by Pascal, Fermat, etc., I hope to gain the gratitude of the whole scientific community by placing before the finest mathematicians of our time a problem which will test their methods and the strength of their intellect. If someone communicates to me the solution of the proposed problem, I shall publicly declare him worthy of praise. I guess women need not apply back in the 1690s. So before I start on the solution to the problem, a little bit of the history first. Let's have a look at a timeline, and like any good timeline, we'll start in the middle, so we can go forwards and backwards from there. In 1696, Johann Bernoulli published this challenge in a journal called Acta Eruditorum, which so happened to be edited by Leibniz, and he posed this problem as a challenge to the mathematicians, but really what they're trying to do was to bait Newton. There was huge animosity between Leibniz and Newton because of what had gone on with the invention and the credit taken for calculus. And Newton at this point was an elder statesman. He was in his 50s, he had retired from being a professor and was now Warden of the Mint, which is something like today's equivalent of Secretary of the Treasury, a position that he would hold on to for the next 30 years until his death. So despite the fact that Newton would go on to live to a ripe old age well into his 80s, and despite the fact that he was the greatest scientist that had ever lived on this planet, science at this point had become a side gig for him. Johann Bernoulli was a man of about 30, and he and Leibniz were keen to egg on Newton, especially since Bernoulli had already found the solution to this problem. In a fitting bit of irony, his solution was actually wrong, or perhaps rather than wrong, it contained an error, and his brother's Jacob was correct. But more on that in a bit. So this idea of posing mathematical challenges in journal publications was nothing new. In fact, about 50 years before that, in 1648, the Tautochrone problem, which is a related problem to the Brachistochrone problem, we'll talk more about that later, but this was a problem that was posed by Pascal in a journal, and it was solved by Christian Huygens. Now, actually, Bernoulli was not the first one to weigh in on the Brachistochrone problem. Back in 1638, Galileo had actually had something to say about it, and he got it wrong. He thought that the best curve was the arc of a circle, but he was able to successfully demonstrate that a curved path was more optimal than a straight path. This challenge was posed in about the middle of 1696, and 6 months later they had received 6 solutions. 5 of those solutions were from household names. I guess if your household is run by mathematicians. Solutions were provided by Johann Bernoulli, by his brother Jacob Bernoulli, by L'Hopital, who happened to be a student, a PhD student of Johann Bernoulli's, Leibniz, and then of course they were successful in egging on Newton. So just to give a little bit of background in terms of the science and theory that was available at the time, Newton in 1676 had published calculus, he and Leibniz independently. And about 11 years later, in 1687, was when Newton published his Principia Matematika, which included his laws of motion and universal gravitation. But the Bernoulli's solution actually relied on Fermat's principle, which was published back in 1662. It's also known as the principle of least time. And interestingly, and I suggest all of you read up on this because it's fascinating, in traveling from point A to point B, light will always follow a path that gets it from point A to point B in the least possible time, and hence the first flavor of a path minimization type problem. And using this principle, Johann Bernoulli was able to come up with a solution. A very elegant solution, mind you, despite containing an error, which was later fixed. So Jacob Bernoulli produces a correct solution, also using Fermat's principle, and Johann Bernoulli tries to pass off Jacob's solution as his own. Well, you can imagine the fireworks that ensued. The Bernoulli brothers were competitive to say the least, and were trying to outdo one another constantly, even though there was 12 years separating them. In an attempt to outdo his brother, Jacob Bernoulli ended up creating a harder version of the Brachistochrone problem, and in solving it, new methods were developed and refined by Euler, which later became the calculus of variations. Unfortunately, Jacob Bernoulli would die at age 50, only 8 years later, and would never get to see much of this calculus of variations materialize. So the story goes that it took Johann Bernoulli 2 weeks to come up with his solution, and Newton, after coming home from the Mint one day at 4 p.m., decided to sit down and solve this, and by 4 a.m. the next morning he had come up with a solution. And Newton had already solved Newton's minimal resistance problem, which is considered to be the first of the kind of calculus of variations. So it took Newton all of about 12 hours. And although Newton published his solution anonymously, it is said that upon seeing the solution, Johann Bernoulli exclaimed, "I recognize the lion by his claw mark." Okay, so this gave rise to the Brachistochrone problem. And then about 10 years later, Leonhard Euler is born. For those of you who are not exactly aware of this, Leonhard Euler is perhaps the best mathematician in history. He's certainly the most prolific, having published over 900 books. He was said to write about 800 pages a year. So Euler is born in 1707. Euler is Swiss and is obviously influenced by the Swiss mathematicians. And in 1726, Euler completes his PhD. And who is his advisor? Johann Bernoulli. His PhD deals with the propagation of sound. It's actually not at all related to the Brachistochrone problem. But then in 1733, he starts working on the Brachistochrone problem. In 1755, along comes Lagrange, aged 19. He's working on the tautochrone problem. Yes, that tautochrone problem from back in the 1640s. He writes a letter to Euler explaining something he's come up with. His solution is purely an analytical one and is different from the solution Euler's working on. Euler is so impressed by what Lagrange presents him that he stops his work. He realizes Lagrange has it correct. Let me give him some time to catch up. Lagrange, by the way, while not quite the mathematician Euler was the master of mechanics, as you're probably beginning to realize. He just was a real prodigy and had a feel for things. And then finally, in 1656, Euler publishes the Calculus of Variations, which provides a framework for Fermat's principle, for the tautochrone problem, for the Brachistochrone problem, and a whole bunch of other path minimization problems. Newton lived well into his 80s to a ripe old age, and he died here in 1726, at about the same time that Euler was completing his PhD. So unfortunately, he would never get to see the Calculus of Variations, although one kind of feels like maybe he had it in his head all along. Okay, so Johann Bernoulli solved this in 2 weeks. Newton solved it in 12 hours. I'm going to solve this for you in the next 10 minutes. But to be fair, I have something on my side that none of these guys had. I'm going to use the Calculus of Variations. Okay, so let's get on with it. The Brachistochrone problem. We've got points A and B, and under the influence of gravity, a marble is going to roll down this frictionless path. From my experience working with this problem, I find that the math comes out the cleanest if we set up our coordinate system as follows, with the origin at point A and the x-axis in its usual direction pointing to the right, but the y-axis pointing down. Proceeding within the framework of the calculus of variations, what we're trying to do is set up an integral I that minimizes the time taken. We want to minimize the integral from 0 to t of dt. Now the time taken can also be written as the integral from point A to point B of ds, the incremental path length, divided by the velocity. And we'll call this equation 1. Now, in order to get an expression for both ds and the velocity v, we can come up with an expression for the velocity v by using the conservation of energy. The kinetic energy of the marble is 1/2 mv squared, and that is equal to the loss in potential energy. Now, because I've defined the y-axis as pointing downwards, that's just equal to mgy. The kinetic energy of the marble is equal to its loss and potential energy. And this can be solved for the velocity equal to the square root of 2gy. To come up with an expression for ds, I've shown this in several videos before, there's a link to that above. We look at an incremental path length, ds. It has a horizontal component dx and a vertical component dy. Then by Pythagoras, we can write that ds squared equals dx squared plus dy squared, and this gives us an expression for ds is equal to the square root of 1 plus y prime squared dx. Let's give these some numbers, 2 and 3, and now what we want to do is substitute 2 and 3 into equation 1. So substituting yields the integral from x1 to x2 of root 1 plus y prime squared dx, that's just ds, divided by the velocity, which is root 2gy. I can simplify this by taking 1 divided by root 2g to the outside, times the integral from x1 to x2 of root 1 plus y prime squared divided by y, dx. From this we can see that the functional in this case is just this pass here. So f is just root 1 plus y prime squared divided by y. Let's number these 4, 5, 6. And I've shown in a previous video, link to that appears above, that in the event that our functional doesn't explicitly depend on x, the Euler-Lagrange equation reduces to something known as the Beltrami identity. The Beltrami identity states that f minus y prime times partial f partial y prime is equal to a constant. And that is equation 7. So all I need to do now is substitute equation 6 into equation 7, and this gives me f, which is just square root of 1 plus y prime squared minus y prime times partial f partial y prime. Well, we can take the 1 over root y out, since that's constant with respect to y prime, and then get 1 half 1 plus y prime squared to the power of minus 1 half. And then we need to take the derivative of the inside, and that gives us just 2y prime. And that's equal to a constant, which we'll call c. Equation 8. Turning the page, we can simplify this equation as root 1 plus y prime squared divided by y minus y prime squared divided by root y times 1 plus y prime squared, and that's equal to a constant, number 9. The first thing I do is I multiply everything by the square root of y. I end up with 1 plus y prime squared minus y prime squared divided by root 1 plus y prime squared, and that's equal to a constant times root y. I'm now going to multiply through by 1 plus y prime squared to clear the denominator. The first term just gives me 1 plus y prime squared. The second term, I just end up with minus y prime squared. And this equals c times root y times 1 plus y prime squared. And that is equation 10. In order to clear the square root, we can square both sides. The left is just simply 1. The right becomes c squared times what's under the square root sign. So y times 1 plus y prime squared. Now I can divide both sides by c squared. I get 1 over c squared, which I'll designate as a new constant that I'll call c1. This is just a constant. And that is equal to, if I distribute it, y plus y times y prime squared. I can rewrite this in terms of y prime, which is of course just dy dx, and that's equal to the square root of c minus y divided by y. Just simple algebra, and that is... Next, we'd like to take everything with an x to the one side and everything with a y to the other side. So that gives us dx is equal to root y divided by c1 minus y, dy. Now what do we want to do? We want to integrate both sides. The left-hand side, dead simple, just x plus a constant. We'll call this c2 since we've already used c1. On the right-hand side, let's just leave this in integral form for now. It's equal to the integral of square root divided by c1 minus y, dy. And now, in order to integrate this bad boy, we need to make a useful substitution. We just substitute y is equal to c1 sine squared theta. In this case, theta is between 0 and pi by 2. And taking the differential of both sides, we get dy is equal to 2c1 sine theta times the derivative of sine theta is cosine theta d theta. Let's give these some numbers, 12, 13, 14, and 15. And now what we'd like to do is substitute 14 and 15 into 13. Making that substitution yields the integral of root c1 sine squared theta divided by c1 minus c1 sine squared theta, where I've just substituted for y, and that is times dy, which is all of that, number 16. We recognize that what's in the denominator here, using a trig identity, can be written as c1 cosine squared theta, because we know that 1 minus sine squared theta is cosine squared theta. Now the c1's cancel, so what's left under the square root sign is just sine squared theta divided by cosine squared theta. So that reduces to sine theta divided by cosine theta times the rest of it. The cosines cancel and the sines multiply, and we end up with the integral of 2c1 times sine squared theta d theta. Using another trig identity, we can rewrite sine squared theta as 1/2 of 1 minus cosine 2 theta d theta. And now this is easy to integrate. That's equal to c1 times theta minus 1/2 of sine 2 theta. And that's number 17. Okay, I hope I'm not losing you guys because we're just about there. I can now rewrite equation 17 in terms of x by just taking c2 to the other side. We'll do that on the next page. And that gives us x is equal to c1 theta, just multiplying it out, c1 theta minus c1 over 2 times sine 2 theta minus c2. And we also have an equation for y. Remember, this comes from equation 14 where we made the substitution. Y is equal to C1 sine squared theta, which can be rewritten as C1 over 2 times 1 minus cosine 2 theta using a trig identity. And that's it, we're done. Let's put a red box around that, give it some numbers. And then, of course, C1 and C2 can be found using the boundary conditions. Now, these equations, 18 and 19, are known to be equations for a cycloid. It's a shape known as a cycloid. And this is the parameterized form of the cycloid equations because it's written in terms of the parameter theta. What is a cycloid? Well, if we take a straight line and we roll a disc or a wheel along that, if we mark a point on the perimeter of the wheel, as that wheel rolls, a cycloid is the path traced out by that point. Looks something like that. And then I was able to find some graphics online that further illustrate this. So a cycloid is the shape that this point makes while rolling along a straight line. If it was rolling along a curve, it would be called an epicycloid or a hypercycloid, depending on whether it was inside or outside the curve. And going back to the original problem, which was trying to find the fastest path from point A to point B, the answer is it's the cycloid through those 2 points. So this cycloid curve from point A to point B represents the minimum time curve. And what might be interesting to some of you is if this were ground level here where point B is, the minimum time curve is actually a curve that goes underground and back up again. All right, so we're done with this. This is the Brachistochrone problem, and this is what prompted the discovery of the calculus of variations. It took about 60 years from the time Bernoulli posed this problem until the time Euler published the calculus of variations. One can only imagine how much quicker all of this would have gone if these guys could have jumped on a Zoom session and done a screen share with one another. Before we go, I want to take it from the top one more time and just review this really quickly. We solved this problem by using the calculus of variations, which requires us to find an integral that we're trying to minimize. In this case, the integral was a minimum time integral, which we could write in this form ds divided by the velocity, and that gave us this final form. From that form, we identified the functional. We recognized that because the functional doesn't explicitly depend on x, therefore we can use the Beltrami identity. That's the form that the Euler-Lagrange equation reduces to in this case. We substituted our functional into the Beltrami identity. We integrated it by making a substitution over here. And when we performed the integration, we ended up with an equation describing a cycloid. Before we leave, I mentioned I would talk a little bit about the Tautochrone problem later. The solution to the Tautochrone problem also happens to be a cycloid, and what the Tautochrone problem is it looks for the shape of a curve that no matter where on the curve the marble is released, it will get to the bottom.
Nah, oke. Nah, jadi kan tadi udah siapa si Aziza nampilin ya tadi tentang penurunan tentang cycloid secara matematis. Nah, tapi tetap sih pertanyaan kenapa aplikasi di dunia nyatanya itu apa gitu loh. Mungkin Aziza bisa lihat dari video tadi mungkin bisa disimpulin.
Oke, mungkin kalau dari aku, kalau masalah Brachistochrone itu masalah klasik yang dalam matematika dan fisika yang berfokus pada menemukan jalur tercepat antara dua titik di mana sebuah benda bergerak di bawah pengaruh gravitasi. Jalur yang paling optimal ini ternyata berbentuk kurva sikloid, bukan garis lurus atau parabola yang mungkin kita bayangkan pada awalnya. Mungkin itu dari aku. Ada tambahan yang lain?
Oke, mungkin yang lain ada yang mau nyampein dulu nih sebelum aku nyampein pendapat juga. Atau mungkin nanti aku terakhir aja nggak apa-apa.
Ini aku sedikit menjelaskan ya. Tadi kan kamu tanya, sikloid itu hubungannya apa sih sama kehidupan sehari-hari gitu kan? Nah, yang pertama itu desain roda gigi. Kalian tahu nggak roda gigi? Nah,
Ya, oke, lanjut.
khususnya dalam roda gigi tanpa gigi miring atau involute gear. Roda gigi itu kayak gear gitu loh, Rek. Bentuk sikloid itu memberikan gerakan yang halus dan efisien ya, antara roda gigi. Terus ada desain lampu sepeda. Banyak lampu sepeda yang menggunakan desain lensa sikloid karena sifat-sifat optiknya yang menghasilkan cahaya yang terfokus dengan baik. Terus desain pemadam kebakaran. Beberapa perangkat pemadam kebakaran menggunakan alat pembuka pintu atau perangkat penyelamat yang didasarkan pada prinsip sikloid untuk menembus dan menghancurkan benda-benda seperti pintu atau jendela dengan cepat dan efisien. Terus desain alat musik juga, beberapa instrumen musik seperti organ pipa dan organologi menggunakan prinsip sikloid dalam desain pipa dan katup untuk menghasilkan tepat dan konsisten. Terus aku juga mau jelasin dikit sikloid dengan Brachistochrone problem. Solusi dari masalah tersebut adalah bentuk khusus dari sikloid yang disebut sikloid Brachistochrone. Dalam Brachistochrone problem, sikloid itu jalur tercepat yang akan ditempuh oleh benda yang bergerak dari satu titik ke titik lain di bawah pengaruh gravitasi tanpa hambatan selain gravitasi itu sendiri. Udah sih dari itu. Oleh karena itu, memahami sikloid dan sifat-sifatnya itu penting untuk memahami solusi dari Brachistochrone problem. Dari aku udah.
Oke, mungkin yang lain ada yang mau nambahin?
Sama kayak Bella sih saya takut.
Oke, boleh. Mungkin Ain, Zahra.
Dari aku udah cukup sih kayak Bella dan yang lainnya.
Nah, oke, mungkin di sini aku sebagai penutup ya, karena udah nggak ada yang mau nyampein lagi.
Aku nggak ada sih.
Oke, jadi di sini mungkin aku ya nyimpulin sama mungkin sebagai penutup. Jadi eh, kenapa kita perlu mempelajari suatu masalah yang dinamakan Brachistochrone? Ya, jadi secara singkat, Brachistochrone itu kan artinya itu jalan apa waktu tercepat kan. Berarti kita mempelajari suatu masalah, masalahnya itu bagaimana kita mendapatkan eh, lintasan dengan waktu tercepat untuk sampai ke tujuan. Mungkin terdengar sepele, mungkin terdengar simple, tapi permasalahan ini tuh meskipun udah dipelajari dari tahun 1600, dari tahun 1800 ya hampir 200 tahun yang lalu, tapi sampai sekarang itu masih relevan gitu. Contohnya mungkin kayak tadi yang banyak teman-teman sebut ya, eh, untuk mempelajari suatu gerak yang dipengaruhi oleh gravitasi. Tapi nggak cuma gravitasi sebetulnya. Kalau misalnya kita menganalisis suatu elektron atau suatu benda gitu dalam pengaruh suatu medan gaya, itu Brachistochrone problem ini juga akan berfungsi gitu. Bisa dimanfaatkan masalah ini. Dan solusinya ya salah satunya adalah sikloid itu tadi. Nah, sikloid ini itu biasanya banyak digunakan ya kayak yang tadi disebutin sama teman-temannya sama disebutin Bella tadi tentang gear. Terus ada tadi Aziza juga nyebutin kalau misalnya sikloid itu juga banyak dipakai kayak eh, di pemadam-pemadam atau yang lain itu kan dalam kehidupan keseharian kita dalam desain ataupun yang lain. Selain itu kan masa depan kita ini kan juga banyak kan yang bilang tentang oh kita mau pergi ke Mars, kita mau pergi ke planet lain gitu kan. Kita mau menjelajah ke planet lain. Nah, ilmuwan meskipun relativitas umum ya relativitas umum yang dikemukakan sama Einstein itu udah ditemukan, tapi untuk menghitung jalur roket itu tetap pakai seperti ini gitu loh. Tetap pakai perhitungan dari Brachistochrone problem ini untuk menghitung jarak roket agar roket itu energinya itu efisien gitu loh. Karena kan roket kan juga perlu membawa apa ini perlu beratnya itu supaya nggak terlalu berat, supaya ringan supaya bisa terbang. Tapi dia harus tetap punya energi. Nah, jadi sikloid itu juga nggak cuma dipakai di masa lalu, tapi juga dipakai di masa sekarang dan juga dipakai di masa depan. Jadi kadang sesuatu yang terlihat simpel, sesuatu yang terlihat kuno, justru itu yang bisa membawa peradaban manusia itu ke tingkat yang lebih tinggi gitu. Meskipun kelihatannya itu sederhana, simple gitu. Justru itu yang menjadi salah satu kunci perkembangan peradaban manusia. Jadi bisa disimpulkan seperti itu. Kenapa kok kita itu mempelajari sesuatu yang amat kuno ya, Brachistochrone problem ini. Dan ternyata ya masih relevan gitu loh. Sampai sekarang masih relevan, masih dipakai. Bahkan dalam keseharian kita, bahkan juga banyak gitu pengembangan yang memakaikan konsep Brachistochrone ini. Jadi mungkin seperti itu yang bisa aku sampaikan ya sebagai penutup, dan juga itu juga merangkum dari teman-teman yang teman-teman sampaikan tadi. Jadi untuk menyelesaikan Brachistochrone ini kita harus memahami tentang persamaan Euler-Lagrange terlebih dahulu. Mungkin itu yang bisa kami sampaikan, kami dari kumpulan NIM 2 dan NIM 3. Ya, di sini ada saya Rizky Setiawan, kemudian ada teman-teman saya. Mungkin bisa perkenalan untuk terakhir kali untuk penutup.
Ya, sebentar.
Oke, mungkin langsung aku tutup aja ya. Ini aku Rizky Setiawan dengan NIM akhir 3, kemudian ada AZIZAH YUNE FADJRINE dengan NIM 43, kemudian ada ZUYYINA NURIN dengan NIM 52, ada ZAHRA Nur AZIZAH dengan NIM 32, kemudian ada SALWA SALSABILA Nur Maulida dengan NIM 83, kemudian ada ALFITRIA dengan NIM berapa? Alfit, soalnya NIM nggak ditulis.
62.
Ya, dengan NIM 62. Jadi mungkin yang dapat kami diskusikan ya pada pagi, siang, atau sore ya, tergantung dengan pemirsa yang lihat di YouTube ya saat ini. Tentang sikloid dan Brachistochrone problem. Kurang lebihnya mohon maaf. Sekian dan terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Stop record ya.